have already been uploaded to the website, so you can download it. Again, do not mind too much about the settings, just do it independently, and I think you may gain something from it. So now let's continue our presentation on chapter 5.
Okay. After that, problem number 4, I did some research on the internet and say that we find first the characteristic equation, and then substitute in this equation the result, and it has to be 0. Is that one?
Yes, the Kelly-Hamilton theorem. Yes, sure. But you must be very careful with the Matlab command. And in fact, there are 2 commands which can be used for matrix polynomial-like things. One is poly-val M. That works only for double precision matrices. It will not work for the symbolic variables. But you can modify it slightly and put it in then you can extend it to a Matlab function in this directory, and you can rewrite it. I think you can solve the problem. The other one is poly-val. This function works only for dot operations. A1 times x or A dot n. Dot power. Not the power itself, so this one doesn't work for this problem. 1, 2, and 3, which the code I provided you, but it's called poly call in this directory. And this one will extract the coefficient from the polynomial, and then we can do simple things like this P1 times A to the power of 4, and do this kind of thing, and then simplify the result. It should be a 0 matrix. In the last lecture, we talked something about Fourier transforms. And the Fourier transforms can easily be solved by calling Fourier function or I-Fourier function, which is quite close to the syntax of Laplace or I-Laplace. You can easily perform, you can easily solve the Fourier transformation or inverse transformation problems. And also noted that some of the existing functions the Fourier function may not work for some of the functions. So one must be very careful with them. We cannot do anything to that kind of problems by computer. And there are also other kinds of Fourier transforms, for instance, Fourier sine transform or Fourier cosine transform. And these are the formulas. And if you solve it using a low-level Matlab command, you can do the integral directly. You can solve the integral problem directly. Or you can call a maple function, but with new versions of Matlab, it is not allowed to do this kind of transformation call. So this is one way. The other way is just to use the definition for f times cosine, and then we take integral from 0 to infinity. Then you can find the Fourier cosine transform. If you replace sine here, you get Fourier sine transform. And again, I don't think there is a way. If you use n here, I don't think you can find the general solution of it. So for this example, if you want to find the Fourier transform to such a function where n equals 1, 2, or other values, and a is a positive number, how can you guide the general form of Fourier cosine transformation of it? The idea is you have to try different values for n and see the result and see whether you can extract something. You can find the relationship from the result for different values of n. One method. And from the result, you may extract something useful to express the general term for different for the n and the formula. So you can derive formulas from it. And this is the Fourier sine transform, Fourier cosine transform. I will explain the result later to you. And also we can take discrete Fourier sine, the cosine transforms. And these are the definitions. From it, we can see that again we can use standard integrals for this kind of problems. And these are the theoretical way to derive discrete Fourier transforms. And in applications, we usually perform fast Fourier transform for given data sets. And this will be discussed later in chapter 8.